the invitation to speak at this session. I'm going to be speaking about something which is perhaps a bit removed from some of the other talks, but bear with me. So here's a quick outline. First, I'm going to tell you about gases of bosons. You don't need to know anything about this subject. Be self-contained. And then I'm going to transition in the first part to talking about the old perspective for studying effective equations for these gases, focusing on a toy model, which is the Lieb-Winninger model. And then in the remainder of the talk, I want to develop a new perspective that's emerged over the last couple of years as part of an ongoing collaboration with Donald Mendelsohn, Andrea Namad, Natasha Pavlovich, and Giulio Staffelani. So gases of bosons. In quantum theory, there's two types of fundamental particles, bosons and fermions. So what are bosons? They obey what's called Bose-Einstein statistics. They can occupy the same quantum state. They have integer spin. Generally speaking, they're force carriers. That means they mediate the forces between other particles. And examples include, things like photons and the well-known Higgs. So in contrast to bosons obey Fermi-Dirac statistics. They cannot occupy the same quantum state. This is the Pauli exclusion principle. They have half integer spin. They're typically building blocks of matter, and an example is electrons. So in this talk, we're interested exclusively in bosons. So, imagine we have a gas of bosons, a Bose gas, which is dilute. So below a critical temperature, this is characterized by a large fraction of the particles occupying the lowest quantum state. And you can have quantum mechanical effects which are visible at the macroscopic scale. And this phenomenon is known as Bose-Einstein condensation, which some of you may have heard of. It was predicted first by Bose and Einstein in the 1920s, but it wasn't experimentally realized until several decades later, independently by Cornell and Weinman and Ketterle et al. And this ultimately led to the 2001 Nobel Prize in Physics. It was mathematically proven, like a theorem, by Elliott Lieb and collaborators in the early 2000s. And below, I've just included, since I'm from MIT, an old picture of the experimental apparatus that they used for sodium atoms to realize a BEC. So how do we describe or put math to this problem? Well, the starting point is, imagine we have n bosons. They're identical in RD. And we want to write down the Schrodinger problem for the wave function of these bosons. So this is described by some function phi n, which is in L2. And it has a symmetry property, which is invariant under permutation. And this is reflecting the fact that we're dealing with bosons as opposed to fermions. So let's assume that this system only has two body interactions, and they're given by some pair potential Vn. In principle, particles have higher order interactions, but typically we argue that those are negligible. And so we just say there are two body effects that we consider. So, okay, we have to write down a Hamiltonian for this problem. And this is given by 1, 2. So this first part, I just have the Laplacian in each coordinate. This is corresponding to the kinetic energy. And then because they're interacting, I have the second term, which is just the interaction between particle I and particle j. And so this notation, Vn xi minus xj, this just means multiplication by this function, Vn little xi minus xj. So in order to study this, we need to impose some sort of scaling limit. So we're interested in initial data, which are factorized. So, the particles are just given by this tensor product of some single particle state. Let's call it phi naught. And if we were to study the time evolution while keeping the number of particles fixed, then, it's too naive a guess to expect that this also remains factorized. This is not true because, you have correlations between the particles due to interactions. And there's no reason to expect any sort of factorization as we send the number of particles to infinity without imposing some regime to study this system. So let's consider what's called the weakly interacting regime, where the kinetic and potential terms in the Hamiltonian are of the same order in n. And it's become common, for reasons I can't exactly tell you, to choose the potential to scale in this fashion. So we're just rescaling B by this nd beta, where beta is some parameter which tunes the strength of the interaction. And then we're dividing this by 1 over n here. And that's to reflect, to balance the kinetic and potential terms. So, if beta is positive, this is kind of, what are the different regimes you can consider? Well, the first is beta equals 0, and this is just called the mean field regime, where the effect is just average between the particles. The next is when beta is positive, but strictly smaller than 1 over d. And this is called the mean field plus sometimes, because mathematically it's not too different than the mean field regime. You expect the same results. This threshold 1 over d is significant because n to the minus 1 over d is the typical interparticle distance if you say have n particles in a box with length size 1. The next regime is the so-called dilute regime. And this corresponds to when the gas or the interactions are on a scale which is much smaller than the typical interparticle distance. And then the most challenging regime is the Gross-Patafsky regime in dimensions d equal 3. There's also a 2D case, but I'm omitting that. And this is special because, well, the length scale of the interaction is of the same order as the scattering length of the potential. So how do we actually obtain a guess for effective equation? Well, we can take the energy per particle of the system, which is just take the Hamiltonian and then take its expectation and divide by the number of particles. And let's make the ansatz that the n-body wave function is factorized and just substitute that in. Then it's an easy calculation to show that as you send n to infinity, you obtain this energy on the right-hand side. So some of you may recognize this as just being the energy for the nonlinear Schrodinger type equation that's given by 1/6, where if beta equals 0, we just have convolution with v, whereas if beta is positive, then v beta becomes just a delta potential as n goes to infinity. So, this is usually called the Hartree equation if beta equals 0. Well, if beta is positive, this is the cubic nonlinear Schrodinger equation. So this naive guess is that we have this approximation where phi n, the n-body wave function, is approximately just given by the n-fold tensor product of the solution of the nonlinear Schrodinger equation. Okay, this is a good first guess. It's at least getting us in the right direction, but it's not clear at all in what sense this approximation holds. And also, we need to be more considerate of the value of beta when it's strictly greater than 0. We may have correlations that persist in the limit depending on the regime, which renders this guess here incorrect. Actually, we know this mathematically in certain cases. So what's actually known about this topic? Well, there's been a ton of work in recent years on rigorously understanding equations such as the NLS and Hartree, which are PDEs, nonlinear PDEs, as effective equations for interacting bosons. This goes back to the 1970s and beginning in 1980s with work of Hep, Ginevra, Velo, and Spohn. It then was sort of dormant, but experienced a revival in the early 2000s, in particular, a landmark series of results by Erdős, Schlein, and Yao, which really got people interested in it afterwards. And then in the years since, there's just been countless work. There's far too many teams for me to attempt to list right here. I emphasize, though, that the overwhelming majority of this activity has interpreted deriving an effective equation in terms of dynamics. So what do I mean by that? Well, showing a solution to one equation converges to a solution of another. And I'm going to refer to this as the old perspective in this talk. But we're going to advance a new perspective as well on deriving an effective equation which focuses on structure, in particular geometric structure. And that will be the second part. So old perspective. And I want to illustrate this old perspective with the Lieb-Winninger model, which is for a one-dimensional system on the real line for bosons that interact via this delta potential. So C is a constant, it's the coupling constant, and it determines whether the system is repulsive, C positive, attractive, C negative, or non-interacting, C equals 0. Non-interacting case is trivial, so let's not talk about it. So this expression 2(1) is completely formal as an operator on L2, but you can rigorously make sense of this just by means of quadratic forms. It's named for Lieb and Winninger, who actually showed that in the periodic case, this model is exactly solvable by a technique known as beta ansatz. And it was originally introduced as a toy system, but it's actually turned out to be extremely useful, as evidenced by a large body of work in the physics literature used to model quasi-one-dimensional dilute Bose gases. And this is actually an example from an experiment showing you a cross-section of the density of a Bose-Einstein condensate that was realized in a lab. You can see the quasi-one-dimensionality because it's very sort of concentrated around this line running parallel to this y-axis. So we're studying this in the mean field regime. And you'll recall from sort of the introduction I gave in that the starting point is a Schrodinger problem for n particles. So that's just, I partial t phi n is equal to the Hamiltonian applied to phi n. And we have some initial datum, which is factorized. So we want to seek an approximate description of this dynamics, which is valid for large n. And we're going to do that by imposing the mean field scaling regime, where we choose the coupling constant C to be equal to kappa over n, where kappa is just say plus or minus 1. This doesn't have to be plus or minus 1. The interesting thing is whether it's positive or negative. It just means that this is of the order 1 over n. So based on the earlier observations, our guess is that this system is effectively described by this one particle nonlinear PDE, which is the 1D cubic NLS. So this is, we believe, going to describe the dynamics of it's going to describe the state of a single particle in the system for large n. So this is giving some meaning to that notion I wrote, or the imprecise relation I wrote earlier, where the capital phi n was approximately equal to the n-fold tensor product of the little phi. So we don't expect all the particles in the system to be close to this state phi. So we only track finitely many degrees of freedom. And we do that by considering the k particle reduced density matrices. So we take the density matrix associated with the n body wave function and trace out the k plus 1 through n coordinates. So you can compute the equation satisfied by this sequence, gamma nk. It satisfies what's called the BBGKY hierarchy. And formally, this converges to a solution of what's called the Gross-Patapsky or GP hierarchy, which is an infinite system of coupled linear partial differential equations given by 2 phi. So this is just the linear part, or excuse me, this is corresponding to the kinetic energy part here. And then you have this term right here, which is coming from the interaction. So if you substitute into this equation an ansatz, which is just each gamma k is this density matrix given by phi k, the k-fold tensor product of phi, then you can show that phi has to solve the cubic NLS in order to get a solution to this equation. So that's confirming our earlier prediction. So what do we mean by actually rigorously establish the mean field limit? Well, we need to show that for every k and n, that we have this convergence. The k particle reduced density matrix for a finite number of bosons becomes factorized in the traced sense as the number of particles goes to infinity. And ideally, we would like a rate of convergence for this expression. How fast does this go to 0 as n goes to infinity? Okay. So in the interest of time, I'm not going to go through this in detail. I'll just briefly say that what's known about this problem, well, there was a partial result by Adami, Bartels, Golson, theta. They couldn't prove this mean field limit, though, in the sense that I just described. This was ultimately shown by Amari and Berthaud several years later using quantum field theory techniques. But there's no sense in how fast this convergence holds. In other words, it's not a quantitative rate of convergence. It just says that the reduced density matrices become factorized as n goes to infinity, but you don't know how fast. So that leads us to the first result that I want to share, which is providing a rate of convergence for this factorization of the reduced density matrices. So I don't want to read the statement in detail for the theorem for you, but we saw this expression before. We need to show that this goes to 0 as n goes to infinity, and we want to show how fast. And the rate that we have is n to the 1 over 6. This assumes some regularity for the limiting initial state. But that's less important. And again, what is phi here? Phi is the solution to the 1D cubic NLS. So this establishes mean field convergence of the Lieb-Winninger model to the 1D cubic NLS with an explicit rate of convergence. And this is both for the repulsive and attractive settings. The sign of kappa doesn't matter. N to the 1 over 6 is almost certainly not sharp. That's an interesting question to improve it. It should be something like 1 over n, ideally. But that's a harder question. So in the interest of time, I don't really want to go into the proof of this result because I'd rather tell you about the new perspective and the remaining part of this talk. So I want to start by recalling what is a Hamiltonian PDE. So Hamiltonian PDE are evolution equations, which arise as models of physical systems exhibiting at least one conservation law. So these have their origins in Hamiltonian mechanics and the theory of finite dimensional Hamiltonian systems. And these Hamiltonian PDE describe diverse physics. They're everywhere. For instance, in fluid mechanics, things like the KdV equation, the Euler equation, even the water waves problem, plasma physics, such as the Vlasov-Poisson and Maxwell-Vlasov equations, and quantum many-body systems, as we just saw with the Hartree and nonlinear Schrodinger equation. So what does it actually mean for a PDE to be a Hamiltonian? Well, there's two ingredients. The first is you have some Poisson manifold structure, and that consists of an underlying manifold, some sufficiently nice algebra on your manifold, which consists of the observables for your system. These are just, say, smooth functionals, real valued on your manifold. And importantly, the skew symmetric bilinear map, which is a bracket that satisfies three properties, what's called the Jacobi identity, a Leibniz rule, and what's also importantly, the existence of a Hamiltonian vector field. So this is called a Poisson bracket. This is just the infinite dimensional generalization of everything you've seen before for finite dimensional Hamiltonian ODEs. So the second ingredient is, of course, a choice of Hamiltonian functional. So this is some element, let's call it H, that belongs to our observable of algebras. And how do we actually get a PDE? Well, we say a PDE is Hamiltonian if it can be rewritten as the infinite dimensional ODE d phi dt is just equal to the Hamiltonian vector field of H evaluated at phi. In other words, you're flowing along the Hamiltonian vector field of H. So let's now recast the NLS as a Hamiltonian PDE. So you'll recall the cubic NLS that we saw before, except now I'm not limiting to dimension one, it may be any dimension. So we need two ingredients. The first is a weak Poisson manifold and a choice of Hamiltonian functional is the second one. So how do we get the manifold? Well, let's just take the Schwartz space that we all know, and let's endow it with the standard weak symplectic structure, where we just take the L2 inner product and we take its imaginary part. So how do I get, what are my observables? Well, we'll just say that they're sufficiently nice, smooth functionals on the Schwartz space. These have what's called a symplectic gradient, called grad SF, which is a smooth vector field on the Schwartz space. And this is uniquely defined by the property that if I take this vector field and I plug it into my symplectic form, then this is just the Gateau derivative of the functional f evaluated at the point phi. Delta phi is just any perturbation right here. So if you have a symplectic structure, that's actually a stronger statement than saying you have a Poisson structure or a Poisson bracket. If you have a symplectic form, it canonically induces a Poisson bracket. And we can do this for the L2 case just by, we get a Poisson bracket by taking any two nice enough observables, F and G. And we just define their L2 Poisson bracket to be the symplectic form evaluated at the grad SF and grad SG. Okay. So our algebra of observables is just going to be something nice enough to ensure that every element has a symplectic gradient. And crucially, our choice needs to include this Hamiltonian that we saw earlier for the cubic NLS. And it's a direct computation to show that the vector field of this choice of Hamiltonian is just given by the right-hand side for the cubic NLS. And so we can rewrite the equation in the form that I described exactly before. So, okay, in the first part of the talk, I was saying, how do we go from quantum many-body systems to the cubic NLS? And I did that by means of starting from the Schrodinger equation for n bosons. And then we looked at the reduced density matrices associated with the Schrodinger equation. And I told you, perhaps too quickly, that this satisfied another system of partial differential equations, which is the BBGKY hierarchy. And then I told you that as you send the number of particles to infinity, you get another hierarchy of equations, which is the Gross-Pitaski hierarchy. So now you have infinitely many of them. And that if I assume that I have a factorized solution of the GP hierarchy, then I recover the cubic NLS. So, okay, and then we just talked about Hamiltonian PDE. And a priori, those two have nothing, it seems, to do with one another. But there are several questions that we can ask to connect the two. The first is, well, can this GP hierarchy, which seems important in the derivation of the cubic NLS, itself be realized as a Hamiltonian system? And can we actually derive such a structure for the GP hierarchy from corresponding structure at the n particle level? In other words, derive the Hamiltonian structure of the GP hierarchy, from the underlying Schrodinger problem, because that's the underlying physics here. And the second question is, well, if the answer to the first question is yes, is there then a natural way to connect the Hamiltonian formulation of the GP hierarchy with the Hamiltonian formulation, the NLS? So this is a geometric Hamiltonian analog of the relationship that we saw earlier, that factorized solutions to the GP hierarchy are just given by taking the n-fold tensor product of, k-fold tensor products of solutions to the 1D cubic NLS. So why should you care about answering these questions? Well, I argue that they're not merely aesthetically pleasing. The Hamiltonian structure completely determines the behavior as a dynamical system. And understanding how geometry arises from physics is a key to understanding how complex behavior is a limiting effect to the underlying system. And in physics, it's a general principle that we obtain new field theories by deformation, examples of which are first and second quantization of a Hamiltonian structure. But ideally, we would like to know if this process is reversible. If we quantize something, can we then find another scaling regime where we can undo what we just did? So what can we say about these questions? Well, we have affirmative answers to both of them. We can show that this BBGKY hierarchy that I mentioned before is itself a Hamiltonian equation. And we can show that this Hamiltonian structure for the BBGKY hierarchy converges to a Hamiltonian structure for the GP hierarchy. And then we can obtain the Hamiltonian structure for the NLS from that of the GP hierarchy via the pullback of some natural embedding. The strategy of the proof is, well, it's actually guided by this approach to deriving the dynamics of the cubic NLS from that of the underlying Schrodinger problem by means of this BBGKY hierarchy. But we then depart from the traditional line of work in the old perspective by using ideas from geometry on Lie algebras and their associated Poisson manifolds. This is the so-called Lie-Poisson construction. We take inspiration from the physics literature, in particular through work of Marsden, Morrison, and Weinstein from the 80s on the Hamiltonian structure of classical particle systems. And our functional analytic toolbox consists of the formalism of weak Poisson structures due to Neve, Solomon, and Thielman, and the Schwartz-Grothendieck theory of distributions. So I think everybody knows about Schwartz's contributions to this subject, but perhaps less well known are Grothendieck's contributions, particularly concerning topological tensor products. So I think the main takeaway here is that our work, especially in contrast to what we saw when we discussed the old perspective, provides a new perspective on what it means to derive an equation from an underlying physical problem. In particular, a perspective focused on deriving underlying structure, geometric structure. So I don't have time to go into further elaboration of each of these points right here. But in the remaining few minutes, I want to just briefly say something about the second part of this new perspective, which focuses on integrability. So what is an integrable PDE? Well, it's a special class of equations which, broadly speaking, can be solved explicitly. And I think there's multiple ideas about how to interpret this, but often solving explicitly for a PDE is usually means the inverse scattering transform introduced by Gardner, Green, Kruskal, and Murrah in the 60s. And then this was reformulated by Peter Lax in terms of the Lax pair. There's been, a 50+ year debate over what it exactly means for an equation to be integrable. There's a whole book by Zaharov that's titled "What is Integrability?" But consensus holds that certain equations should be integral under any reasonable definition of the term. And two examples are, for instance, the KdV equation, which was shown to be integrable by Gardner et al., and the 1D cubic NLS, which we've saw multiple times before, which was formally shown to be integrable by Zakharov and Shabbat. So despite vast research on the implications of integrability, it remains unclear, at least to me and my collaborators, why equations which are so physically ubiquitous happen to be integrable in the first place. Especially that integrable PDE are very special. You perturb an integrable PDE, it's most likely not going to be integral anymore. So related to this, Calligero advanced the thesis that equations are integrable because there are scaling limits of integrable or conjecturally integrable systems, which we'll call progenitor models. So let's now reconsider the 1D cubic NLS from the viewpoint that it arises as the mean field limit of the progenitor Lieb-Leininger model. So I mentioned earlier that the Lieb-Leininger model itself is exactly solvable. This was originally shown by the eponyms for the model. This leads us to the following conjecture, that the integrability of the NLS follows from the exact solvability of the Lieb-Leininger model. And therefore, we expect evidence of integrability at the level of this GP hierarchy, which is relevant for the derivation of the cubic NLS. So the goal, accordingly, is to provide evidence for the GP hierarchy as a new integral system itself. So how do we interpret integrability here? Well, for us, this is going to be in the sense of u vil. And what does this mean? Well, for finite dimensional Hamiltonian systems, we say that it's u vil integrable if you have a maximal, in the sense of degrees of freedom, independent set of Poisson commuting integrals. And why is this useful? Well, under some technical conditions, if this holds, you can solve your system exactly just by making a change of coordinates to action angle variables. So the NLS is formally integrable by the IST. Zakharov and Shabbat showed this. And this has been mathematically revisited by numerous people over the last 2 decades. And the consequences of being solvable by the IST are that the Hamiltonian is one element of a countable family of functionals which are in mutual involution. They Poisson commute. So how do you get these functionals? Well, there's a recursive scheme. It's just given by here. You can find this in, say, the book of Fadiev and Takhtajan. So each of these generates a real valued functional. It's called IN, just by integrating this density against phi bar. And you can check, maybe it's a little bit more than just checking, that each of these INs, they commute with each other with respect to the L2 Poisson bracket. So, okay, now you could choose each of these INs to be a Hamiltonian and then compute the corresponding Hamiltonian PDE associated to it. And altogether, this forms what's called the nonlinear Schrodinger hierarchy. The third element is just the NLS, while the fourth is the complex MKDV. So this leads us to motivating questions that I'll conclude with. In light of this preceding discussion and our search for evidence of integrability for the GP hierarchy, we can ask the following. Does the 1D cubic GP hierarchy itself possess an infinite sequence of functionals Hn, which contain the Gross-Patowsky Hamiltonian and which are in involution with each other? And can we actually relate each of these Hn to the functionals In that I just showed you before for the NLS hierarchy? And the second question is, well, does each of these Hn generate a Hamiltonian equation of motion that's somehow related to the nth element of this nonlinear Schrodinger hierarchy via factorized solutions? We already saw this equation when n equals 3. That was just the cubic NLS case. And what about if n is not equal to 3? So why is this important? Or an important observation here is that these questions only make sense because we have a geometric structure for the GP hierarchy. That's what I told you about before we started talking about integrability. So I'll just end by saying that we answer both of these questions in the affirmative. We can construct these functionals. We know what they look like. There's a recursive scheme. A lot of the ideas for doing this are by quantizing what is known for the NLS itself. We essentially show a correspondence between the integrability of the GP hierarchy and the integrability of the NLS. And understanding or developing this correspondence is the key for the proof, combined with our previous work on deriving the geometric structure. So our work is a first step for showing that the GP hierarchy is itself a new integrable system. And I think I'm out of time, so I should stop there and thank you for your attention.
Thank you very much.